So this video brings some exciting news. We actually are going to introduce two new parent functions, and that would be y equals e to the x and y equals ln x. And so you guys know the previous 9. Let's run through them real quick. Y equals x squared, y equals, say them with me, absolute value of x, y equals x cubed, y equals square root of x, y equals cube root of x, y equals 1 over x, y equals 1 over x squared, and the ceiling function, is that all of them? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So we have 10 and 11 here. So you guys know how the exponential works. I mean, you know that this is just telling me how many times I multiply by e. So if I put a 1 in there, that'd be e. Put a 2 in there, that'd be e squared, etc. E is probably not something you recognize. E is equal to approximately 2.71 something something something. It's all over your calculator. There's an e button, there's an e to the x button. It's a number like pi that occurs in nature and finances and a lot of different places. So we've actually given it a name. So this ratio, 2.71 something something something, actually is all over the place. So let's take a quick look at the graph of this thing. Whoa, that was a non-straight line. So the graph of this thing, y equals e to the x. So if you plug a 0 in for x, we all know that anything to the 0 power is 1. So that would be right there. And if we plug in bigger and bigger numbers for x, it's just going to get bigger and bigger and bigger. So e to the e squared, that'd be like 2.71 squared, so that's going to be a little bit less than 9. And e cubed, that's going to be 25 or 6-ish, etc. So essentially what happens is this thing just shoots off into space. Now if you go on the other side, if we start plugging in negative numbers for x, that's going to be 1 over e squared, 1 over e cubed. So that's going to get smaller and smaller and smaller, and what happens is it just heads down here. And we discover there's an asymptote, a vertical asymptote. Horizontal asymptote. There's not a vertical asymptote over here. This just gets bigger and bigger and wider. But it gets big a lot faster than it gets wider. But this does get smaller and smaller. It gets closer and closer to 0. It'll never turn negative. So we have a horizontal asymptote on the x-axis, and this is shooting off into space. So if we were to talk about the intercepts of this thing, it does not have any x-intercepts because it never crosses the x-axis because there's an asymptote there. If we talk about y-intercepts, of course it's just 1, we can see that. In behavior, we can see that this is kind of an interesting one because it's different. In behavior, on the right, it's headed towards infinity. On the left, it has a horizontal asymptote at y equals 0. So this is the first one where we have horizontal asymptote on one side and not on the other. So that's kind of an interesting, unique thing. And notice we can do all the reflections of this. If we do y equals e to the negative x, that would be a inside negative. So that would be a reflection across the y-axis. So you could probably picture that pretty easily. Instead of going here up, it's going to go from here like that. So the horizontal asymptote is on the right now, and then positive infinity is on the left. Yeah. So if we put a negative out front, for example, y equals negative e to the x, that also would be a reflection across the x-axis. So then what happens is we have something that looks like this. Oops, that should be steeper. There we go. So you can play around with that some, but that's the basic parent function, y equals e to the x. Likewise, we have the natural log, and the cool thing is the natural log is, I'm going to grab a different color here. Let's go with blue. natural log is the inverse of e to the x, which means if we think graphically, we could we could reflect it across the line y equals x. Remember in the last video I said that inverse function is the reflection of the original function across the line y equals x. So this point would reflect right to here. In fact, if you paid attention in the last video, I actually did this same thing already. Just didn't call it these two functions. And this would come up like that, and we'd head off like that. So this is the graph of y equals ln x. And essentially ln x is defined in that it undoes e to the x. So if we had the natural log of e to the x, that would just be equal to x. The natural log undoes e to the x. Okay? So that's the basic parent functions, and now we're going to I'm going to focus a little bit more on the exponential family, because really the logarithmic family just is kind of defined by the inverse of the exponential family. So in general, the exponential family can be fit into, or this is the general form of the exponential equations. Of course, I could have a plus or minus up here or a plus or minus out there, but this is the basic general form of a exponential equation. And the graph of that thing is, as it's written, is like the e to the x, going to look something like this. And notice that in this case, the a would be like the stretch factor, right? So we know that if we plug in a 0 for x, then we get 1 for this. And so this point right here will always be a. So in this general form, we say that a is the y-intercept, or what we usually call it is the initial value. Because that has some connotations in what's the applications. So, because you can see the a is going to be the y value when x is equal to 0. So that's why it's called the initial value. And the b is called the growth or decay factor. Because the way this thing grows or decays is, if you're multiplying over and over again by b, it's going to get, it's going to grow because you're multiplying by b, or it's going to decay, which means get smaller, depending on what b is. So we'll talk about that for a minute. If b is less than 1, but greater than 0, of course, because at 0 we don't have an exponential function, but if b is less than 1, then we have a decay factor, because you're multiplying over and over again by something that's less than 1, which would make it smaller. And actually, we would have a graph, we would have a graph that looks like this. If b is greater than 1, then we have growth factor. Then it's called a growth factor. Because if I'm multiplying over and over again by something greater than 1, it's going to grow. Right? So a is the initial value, and b is either the growth or decay factor, depending on whether it's greater than 1 or less than 1. And in fact, depending on what b is, for example, if we wanted to compare y equals 3 times 2 to the x to y equals 3 times 5 to the x, how would those two compare? Well, they cross at the same place because 3 is the initial value. They cross the y-axis at the same place. But you could probably tell just by thinking for a few minutes that this one is going to grow faster because you're multiplying by 5 over and over again, whereas this is multiplying by 2 over and over again. So that's an important thing to notice. Likewise, if I was comparing y equals 2 times 3 to the x and y equals 5 times 3 to the x, Well, notice these two are growing at the same rate, but their initial value is different. Right? This one is going to cross the y-axis at 2, that's going to cross the y-axis at 5. Okay. So we got growth factor, decay factor, we got initial value, those are all important things. And moving towards making applications. So another thing that's important is often when we talk about things growing exponentially, we talk about their growth or decay rate. And it's important to understand that's different. That's different than growth factor. Growth factor is the thing in the equation that we've been talking about. So growth factor we know is y equals a times b to the x. Growth factor is the b. Now growth rate is something that might be in an application problem where we say it's growing, 5% a year. Okay, that would be a growth rate. So the question is, how do we translate that into a growth factor? Because if something's growing 5% a year, like for example, let's say you have $1,000 and it's growing 5% a year because you put in some kind of investment thing. That would be awesome if you found something that grows 5% a year right now. But anyway, so let's say you have $1,000 and it's growing 5% a year. So you could easily write a little equation for that because the initial value is 1,000. That's where I start out when time is 0. And we're going to measure time by years. So we're going to put a little t up here, and we'll say t is years since investment. So since I invested $1,000, t is measured the number of years because it's growing 5% a year. If we said it's growing some percentage per month, then we'd want to measure t in months. Okay, so y equals 1,000 times something. Now the key here is that I don't want to put multiply. Now we know that 5% is the same thing as 0.05 as a decimal, right? But we don't want to multiply by 0.05 here because that would just give me how much interest I gained or what the growth is. But what I want to know is how much money I have in my account presently, or how much the total amount is. So the way to do that is we just take 1, because 1 times 1,000 will give me what I have, and then we add to it 0.05. So in other words, I'm taking 105% of what I already have, which would give me the amount I already have plus the growth. So the way you convert between growth rate and growth factor is by adding a 1 to it, adding a 1 to the decimal equivalent. Likewise, if I was comparing decay rate to decay factor, you would subtract it from 1. So essentially, if the decay rate is say 3%, that means the decay factor, the thing you actually put in the equation, would be 0.97 because that comes from 1 minus 0.03. Or you could think of the decay rate is 3%, which means the decay factor is 97%. But of course we change it to decimal equivalent when we put it in the equation. Okay, so that's some vocabulary word. It also is important to understand the connection between y equals, say, 2 to the x and y equals log. Now, up here, we had a natural log. This is ln x, so that's a log that undoes e to the x. And so notice there's no little base down here. So normally, most logarithms have a base. So, for example, we could say log base 2 of x. So to make that comparison, y equals e to the x and ln x. Ln x is the same thing as log base e of x. So essentially, the base tells you which exponential the logarithm undoes. So log base 2 undoes 2 to the x. Natural log undoes e to the x. If I have 5 to the x, then I would need a log base 5 to undo that. Okay, so again, what we're saying is log base 5 of 5 to the x would be equal to x. That's what we mean by undoing it. Just like the square root of x squared equals x. Okay, so if you're dealing with logarithms, which is, those are the things that I think people are most unfamiliar with, you can actually write a logarithm in its exponential form, because this is talking about the base, so that's the base. This is talking about the power, or the thing that it's that I'm the answer in a sense of an exponential equation, and then this, if I don't know it, that is considered the exponent. So in other words, if we want to write this in exponential form, we would say the base is 2, the exponent is x, and that's equal to 3. Okay? So that's taking a logarithmic expression and writing it in exponential form. Let's do another example. If I had log base 2 of 8. Okay? Equals 3. This is a true statement. So this is saying the base is 2, the exponent is 3, and the power is 8. When you multiply those all out, you get 8. Okay, so these two are saying the same information. And that's how we use to evaluate a log, because I think if I just put 2 to the 3rd power on a paper, you would all know that's 8. But if I threw log base 2 of 8 down here and asked you to evaluate, at least a good number of you would say, huh? What does that mean? So the way you want to think about it is, remember that the 2 is the base, the answer to a logarithm is an exponent, and then 8 is truly the answer to exponential question. So again, we can just convert this to its exponential form. So 2 is the base. This answer that I'm looking for is the exponent, and that's equal to 8. So if we're trying to evaluate this, we can say, oh, this is just asking me 2 to what power equals 8? Well, I know that 2 to the 3rd power equals 8. So that means this would be 3. Another example, log base 2 of 1/2. So this is saying 2 to what power equals 1/2. Well, in order to raise 2 to the power to get 1/2, it looks like I'm probably going to need a negative, aren't I? Because there's no way I can raise 2 to a positive power and make it smaller. So this looks like 2 to the negative 1 is equal to 1/2. So that means the answer to this logarithmic question would be negative 1. Another example, log of 1,000. So if you see log without any base, that is generally means log base 10. So if you see a natural log like this, that means log base e. Log without a base means log base 10. Every other logs have a base written in. So this is log base 10 of 1,000. So that's saying 10 to what power equals 1,000. And of course, we just think for a moment, 10 times 10 times 10 would be 1,000. So the answer to that is 3. Okay, so there's some just a little orientation to logarithms and how they behave with exponentials, and they are used to undo them. You also need to be able to put this in your calculator. Now your calculator has an LN button and an LOG button. Again, this is log base e, that's log base 10. It doesn't have a log base 2 or 3 or 4, but we have this thing called the change base theorem. If you have the log base 2 of x, okay, you can change the base of that from base 2 to something else by just taking, say I wanted to change it to base 10. So then I would say log of x divided by log of the base. Or let's say I want to change it to natural log. That would be natural log of x divided by natural log of 2. Or let's say I want to change it to base 5. That would be log base 5 of x divided by log base 5 of 2. So you can take any log of any base and change it to any base you want to in this process. And that's how you would put something like that in your calculator. So for example, if I had log base 3 of 7, of course that means 3 to what power equals 7. Well, I can't do that in our head, so we need a calculator for that. So what you type in your calculator is, for example, natural log of 7 divided by natural log of 3. That's using the change base theorem, and that will calculate what log base 3 of 7 is. Okay, let's go back up to the top here and take a quick look at these things. We never talked about domain and range. So the domain of e to the x is all real numbers. We can see that, right? And the range would be from 0 to infinity, not including 0. And notice, because these are inverses of each other, those would just flip on natural log, right? So natural log, the domain is from 0 to infinity, not including 0. And the range would be all real numbers. So you can see domain here is all real numbers. Yeah, that's an ugly all real number. All real numbers. And the range is from 0 to infinity. And over here, they're flip-flopped. The domain is from 0 to infinity. The range is all real numbers. Alrighty.